Section 3.1 is going to be about the basics of probability and counting. So we're going to start off with a bunch of vocabulary. First of all, let's talk about a probability experiment. A probability experiment is an action or trial through which specific results, such as counts, measurements, or responses, are obtained. Sample space is going to be all of the possible outcomes in a probability experiment. An outcome is the result of a single trial. And an event is a subset of the sample space. And events are often represented by a capital letter. A tree diagram is a visual display of all outcomes. Okay, so let's look at an example where we get to use some of these terms. What we're basically going to be doing here is identifying the sample space for a probability experiment. So here's our experiment. A probability experiment consists of tossing a coin and then rolling a 6-sided dice. Determine the number of outcomes and identify the sample space. So in this experiment, where we are tossing a coin and then rolling a dice, we're going to go ahead and make a tree diagram to represent that. The first event that's going to happen is that we will toss the coin. And when you toss the coin, there are two possible outcomes. The coin could land on the head side or the tail side. So there's our two outcomes. After that first event, then what happens is we are going to roll a number cube. And there are going to be 6 possible outcomes. It could land on a 1, 2, 3, 4, 5, or 6. And also, if it landed on tails, it could also land on a 1, a 2, a 3, a 4, a 5, or a 6. So the sample space is going to be listing out all of the possible outcomes. So when you have a tree diagram, you're kind of looking at the right-hand side here to count up the number of outcomes. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 outcomes. And then the sample space for this experiment is going to be that the coin lands on heads, the dice lands on 1. Or the coin lands on heads, the dice lands on 2. Or the coin lands on heads, dice lands on 3. Or heads and 4. Or heads and 5. Or heads and 6. Or tails and 1. Tails and 2. Tails and 3. Tails and 4. Tails and 5. Tails and 6. So in the sample space, we go ahead and list out all of the possible outcomes of our probability experiment. Now, an event, I kind of briefly mentioned, an event is a subset of the sample space. So one of the events Could have been landing on heads and 5. Another event could be tails and 2. So I'm going to use that to start figuring out probabilities here in a little bit. We have a couple of other examples we can look at. A probability experiment consists of recording a response to the survey that's on the left here, and then the gender of the respondent. So we're going to record a response to the survey and then the gender of the respondent. So our sample space for number 1, sample space, is that the person could say yes and then be male, or the person could say yes and then be female, or the person could say no and then be male, and then the person could say no and then be female, or the person could say, I'm going to use S for not sure and be male, not sure and be female. So in my sample space, I have 1, 2, 3, 4, 5, 6 possible outcomes. On number 2, a probability experiment consists of recording a response to the survey and the geographical location being north, east, south, Midwest, or west. So my sample space here would be saying yes to the survey and then being from the northeast, or saying yes to the survey being from the south, or yes to the survey being from the Midwest, or yes to the survey being from the west. Or I could say no to the survey and be from the northeast, no to the survey, be from the south, no to the survey, be from the Midwest, no to the survey, be from the west. Or I could say not sure and I'm from the north, not sure and I'm from the southeast. Whoop, backwards, northeast, south, not sure, Midwest, and not sure, west. So the total number of outcomes I have there is going to be 12 outcomes. Now, when it comes to events, there's something that's called a simple event. A simple event consists of a single outcome from a sample space. So if you think back to our very first example where we were flipping a coin and rolling a die. So that's, or number cube. That's from example 1. If my event, which we're going to call A, because remember that events are often use a capital letter to notate them. So if my event is H3, then what that means is that the coin lands on heads and the dice lands on 3. And event B is H and odd. We want to know, are these simple events or not simple events? So a simple event consists of a single outcome from a sample space. So H3 is a simple event because there is only one relevant outcome in the sample space. If we look back at our sample space from example 1, H1, 2, 3, all of those sample space, if my event A is H3, only one of those events is relevant to that outcome. But in event B, if the event is heads on the coin and odd, then if I look at my sample space, H1 would be heads and odd, H3 would be heads and odd, H5 would be heads and odd. So this is not a simple event. because H1, H3, and H5 are 3 relevant outcomes in the sample space, not 1 relevant outcome. So let's do some more practice in identifying simple events. Determine the number of outcomes in each event, then decide whether each event is simple or not, and explain your reasoning. So, for quality control, you randomly select a machine part from a batch that has been manufactured that day. Event A is selecting a specific defective machine part. So is this a simple event or not a simple event? Event A is selecting a specific defective machine part. That makes it a simple event because it's referring to a specific part. How about example 2? You roll a 6-sided die. Event B is rolling at least a 4. So event B would be rolling at least a 4. So what outcomes could go with at least 4? Well, that would mean it would be a 4 or a 5 or a 6, which makes event B not simple because there are 3 outcomes that could go with that description. Let's just make up another little example to go along with this, just for more practice. If you ask people their age, then event C is going to be that the age is between 16 and 19 inclusive. Okay, what does that mean? What does inclusive mean? Inclusive means that it's between those 2 numbers, but it also includes those 2 numbers. So would this be simple or not simple? Event C would be not simple because there are 4 outcomes that go with that event. You could be 16, 17, 18, or 19. What about event D? Event D is the age is 18. Well, event D would be simple because there's only 1 outcome that fits that description. Hopefully that helps explain a little bit about simple and not simple events. Let's talk about the fundamental counting principle. The fundamental counting principle is going to help us figure out how many ways 2 or more events can occur in a sequence. So the fundamental counting principle is used to determine the number of ways 2 or more events can occur in a sequence. So just for simplicity, I'll give you kind of the formula for 2 events. So for 2 events, if the first event can occur in m ways, and the second event can occur in n ways, then there are m times n ways for the 2 events to occur in sequence. So that's going to help us determine how many outcomes there would be in a sample space. So think back to our flipping a coin and rolling a number cube. Flipping a coin had two possible ways that could happen, heads and tails. And rolling a dice could happen in 6 ways. So if I take 2 times 6, that gives me the 12 that I had for the number of outcomes in my sample space. But then also realize this pattern can be extended to any number of events. Now let's practice using the fundamental counting principle. You are purchasing a new car. The possible manufacturers, car sizes, and colors are listed. So we can choose from a Ford, GM, Honda. It could be compact or midsize, and we could choose red, white, black, or green. How many different ways can you select one manufacturer, one car size, and one color? So kind of the way that I think about the fundamental counting principle is I need to figure out how many decisions are going to be made, and then I want to know how many choices do I have for each decision. So how many decisions am I making? I'm going to choose one manufacturer, one car size, and one color. So I have 3 decisions. 1, 2, 3. And the fundamental counting principle says that I'm going to multiply the number of ways that each can occur to get the total number of outcomes. So if I select one manufacturer, I have 3 different choices. So I have 3 times, and then I have 2 car sizes to choose from. So 2 choices there, and 4 choices for color. So I'm making 3 decisions, manufacturer, car size, color, but I have 3 choices, 2 choices, 4 choices. So this is going to give me a total of 24 different ways that I could choose a car. Okay, so now we're going to change the problem a little bit. Now your choices include a Toyota and a tan car. So we still have the same number of decisions, manufacturer, size, and color. But now I have 4 choices for the manufacturer. I still have 2 choices for the size, but I have 5 choices for the color. So that's going to give me a total of 40 different ways for me to choose a vehicle. Okay, more using the fundamental counting principle. The access code to a car's security system consists of 4 digits. Each digit can be any number from 0 through 9. So I have 4 different spaces, 4 different decisions to make, and then each decision will have a different number of choices for that decision. So we're going to kind of look at different scenarios. On number 1, we want to know how many different access codes are possible when each digit can be used only once and not repeated. So I'm going to have 4 decisions to make. For the first digit, it can be any number from 0 through 9. So that means that I have 10 different choices for that first digit. But now since I can't repeat on my second digit, instead of having 10 choices, now I have 9 choices. And then on my third digit, since I can't repeat, I've already used 2 numbers, so I have 8 to choose from. And on my fourth digit, I'll have 7 to choose from. So that is going to give me 10 times 9 times 8 times 7, 5,040 different access codes if there can be no repeating digits. What if each digit can be repeated? Well, I still have the same 4 decisions to make, but now, since each one can be repeated, I have 10 different choices in each of those spaces. So that will be 10 to the 4th, which is going to give me 10,000 different access codes. Now, what if each digit can be repeated, but the first digit cannot be a 0 or a 1? So 4 choices. Each digit can be repeated, but the first one cannot be a 0 or 1. So that means it only has 8 choices. Then all the other spaces have 10 because we can repeat anything we want. So that's going to give me 8 times 10 times 10 times 10, which is 8,000 codes. Let's do some with license plates. So number 1, how many license plates can you make when a license plate consists of 6 alphabetical letters, each of which can be repeated? So I'm going to have 6 spaces on my license plate. 1, 2, 3, 4, 5, 6. And each of those spaces is going to be a letter from the alphabet, and they can be repeated. So each of those spaces, each of those decisions will have 26 different choices available. So that's going to be 26 to the 6th power. That's going to be a large number. 26 to the 6th power. Yikes. $308,915,776. Okay, next scenario. On number 2, we're still going to have 6 letters. So 1, 2, 3, 4, 5, 6 letters, each of which cannot be repeated. So my first decision, there are 26 choices. In my second one, I've already used one of the letters, so I have 25 to choose from, and then 24 to choose from, 23 to choose from, 22, and 21. So 26, 25, 24, 23, 22, 21. So now I only have 165,765,600. And then last, we're still going to have 6 letters. Each of which can be repeated, but the first letter cannot be A, B, C, or D. So on my first letter, instead of having 26 choices, A, B, C, and D are knocked out, so I only have 22 choices. And then all the rest of them have 26 choices. So my total number of outcomes will be 22 times 26 to the 5th. So 22 times 26 to the 5th. 2, 6, 1, 3, 9. So 261,390,272.